I will talk about an impurity model called the Spin-Boson model and how we can study its dynamics using real-time quantum Monte Carlo, specifically the inchworm algorithm. This is work done in collaboration with Goulko and Olga Goulko and Theta Chen, and you can read more details in this paper here. So let me first introduce the Spin-Boson model. So it consists of a spin or a two-state system that's coupled to a bath of non-interacting harmonic modes or bosons. And so it's a fixed impurity model, which was originally developed to study dissipation in quantum systems. So since energy is conserved in a Hamiltonian formalism, one way to study dissipation is to couple the system to an infinite bath. And this is sort of the simplest bath you can think of, a bath of harmonic modes. But this model is also very useful to study coupling to photons or phonons, and even electronic systems via mapping called bosonization. So let me present the ingredients of the Hamiltonian of this two-state system. We have first the spin, two-level Hamiltonian. Here epsilon is the energetic bias, and actually I'm only going to talk about unbiased systems where epsilon is 0. Delta characterizes the diabatic coupling, so the tunneling between the two states. The sigmas are Pauli matrices, so overall the spin part of the Hamiltonian is a 2x2 matrix. Then we have the Hamiltonian of the bosonic bath, which is simply a sum of harmonic oscillators. And then finally, we have a system bath coupling, which we assume to be linear. These coefficients, Ck, characterize the coupling strength to the kth boson mode with frequency omega k. And in the condensed phase, we can consider the system to be coupled to a continuous bath. So we can characterize the system bath coupling by a spectral density in this compact form. So in this particular functional form, J is smooth, and for frequencies below a certain cutoff frequency, omega c, it's of the form omega to the power of s. So this omega c kind of defines the relaxation tile scale of the harmonic bath. Now, depending on the value of this exponent s, the system has very different physical regimes. The most studied, perhaps, is the ohmic regime, where s is equals to 1. And we can get a lot of analytical insight into that regime. If s is greater than 1, that's a super-ohmic regime, and it's trivial because in this case, the tunneling always outweighs the weak coupling. So the system is always delocalized or equally likely to be found in either state. What I'll focus on today is the sub-ohmic regime, where s is between 0 and 1, and it's a very interesting regime with a very rich phase diagram. It exhibits a quantum phase transition at 0 temperature and a lot of other interesting properties that I will mention. I also want to mention the initial condition. So here we will use the factorized initial condition. So we assume that the bath is in thermal equilibrium without any system bath coupling, and the spin is held in one of the two states. And then when we turn on the time evolution, we will couple the two. But it's also possible to consider other initial condition. For instance, we could equilibrate the bath together with the system while keeping the system fixed, and then release it and allow it to change. And this will affect the dynamics of the problem. So as I mentioned, we are interested in the dynamical properties of the system. And of course, out of equilibrium, the diagrammatic expansion is much more complicated. So to sketch what I mean here is a generic form of a time-dependent expectation value of an operator. And in the equilibrium case, the time-dependent parts would just cancel each other because we can commute the operators past each other. So we would be left just with an expansion of rho 0 of the density matrix, which we can formulate in imaginary time. But we cannot do that if these operators do not commute. And this can happen for different reasons. For instance, the Hamiltonian could have an explicit time dependence, such as a system being driven by a time-dependent force, or the density matrix can have non-equilibrium correlations if we have, say, a current flowing through the system. So we might not have a notion of temperature at all. Or as in our case, we could have an initial density matrix, which is different from the equilibrium limit. So we have quenched the system into a different state. And this is what is the case in our setup here. So in the general case, we need to account for all operators in the expansion explicitly, and this can be done using the Keldysh technique. For example, here I marked the branches of the Keldysh contour by the corresponding colors. We can start out at the time t max. We can propagate backwards along the blue branch to time 0, to an initial time 0, and then forward again along the red branch. And if we didn't know the initial density matrix, we could add an additional imaginary time branch to the contour. Now, within the Keldysh formalism, we can do a diagrammatic expansion in an analogous way. We can place the vertices now on either branch of the Keldysh contour. The system observable is placed on the Keldysh fold, and then we can sort of unwrap the contour and perform updates in a similar way as we would for usual imaginary time propagators. Now, one crucial difference is the time propagation must be carried out in real time, and this leads to a dynamical sign problem, which can be very challenging. So the big challenge here is how do we perform efficient real-time quantum Monte Carlo updates to address this problem? And one way to do that is the so-called inchworm algorithm that was developed by my collaborator, Guy Cohen. So just kind of to very briefly introduce the main idea behind that algorithm. In each step of the inchworm algorithm, the previously calculated full propagator is extended by just a small amount of time. And the idea is that in this way, we can recycle information from our previously computed bold propagator, and short-term extensions are much cheaper to calculate than long-term ones. And so this has been shown to reduce the scaling from exponential to polynomial. So there are several ways to do this expansion for the Spin-Boson model, and I will show you the two kinds of expansion that we perform in this work. The first is the system-bath coupling expansion, or expansion in the interaction part of the Hamiltonian. That's analogous to the hybridization expansion for fermions if you study the Anderson model. So that's kind of maybe the first thing we think of when we want to do an expansion. And in this case, our setup factorizes into a system part with the system operators, and then a bath part that just contains the bath operators. And here you can, by the way, see all of the details of these expansions with all the derivations and the corresponding math. So schematically, the system part is quite simple because the system part contains the sigma z Pauli matrix. We have a product of matrix propagators that are in matrix form and insertions of the sigma matrix. So we have a matrix system part, but it's actually has a very simple form. And then the bath part is scalar. And we have the usual contributions, the usual combinatorial contributions from Wick's theorem, and we can compute the bath correlation functions in this way. So this system bath coupling expansion works especially well when we're at low temperature and also when we are at weak coupling. We can also expand around the tunneling constant delta, so we can expand around the spin flip part of the system Hamiltonian. And here we observe that if we separate it in this way, H naught commutes with sigma z. So we kind of put all of the sigma z contributions into H naught. And so its eigenstates will maintain the spin quantum number, and this partitions them into two subspaces. So within each subspace, then this Hamiltonian can be diagonalized by a canonical plural transformation. So the system part then becomes simply a sequence of state flips, and then possibly also phase if we have an energy bias. So our sigma x just simply flips between the sigma z eigenstates of the system. And because of our initial condition, we need to start and end in the same state. So if our observable is a default, we can only have an even number of sigma x insertions. The bath, on the other hand, is a bit more complicated. So now it becomes a multi-time correlation function of bath operators. And we can derive a generalized Wick's theorem for this bath. And this is what it graphically looks like. So essentially, we have expressed the bath contributions as a ratio of products of two-time correlation function. And represented graphically, it means that each vertex is connected by interaction lines to each other vertex and also to the initial condition, which is not shown in this sketch. So every configuration is a very big cluster diagram, and this cannot be made, this cannot be boldified efficiently, so it's difficult to cut these diagrams. So we have to do a little bit more to do an expansion with inchworm in this way. And so the first step is to express the diagrams in terms of moments. So for this, we do a partial summation over all possible Keldysh contour branch indices that have the same physical time ordering. So we sort of combine all diagrams with the same physical insertions at the same physical times into one moment diagram. And this means that we only keep even moments. And then we can go a step further and resum these moments again into cumulants. For example, as is shown here. Again, we only have even terms in this expansion. And now in this cumulant form, we can use the bold scheme. Here is a sketch of that, and we can apply the inchworm method in this scheme. So this expansion has some advantages. One advantage is, well, we no longer need to consider the Keldysh branches separately. We have summed them together. So it scales linearly and not quadratically with the time step of the expansion. And that is quite a significant speed up. It's also much easier to continue simulations because we only need to keep track of the observable itself and nothing else. So it can be a very efficient expansion in those regimes where it works. Specifically, it converges better than the hybridization like coupling expansion when we're at high temperatures and at strong coupling. So let me move towards showing you some results. But beforehand, I want to show you just one benchmark, really. So we tested our code extensively in different setups. The observable that we're interested in computing is the non-equilibrium population difference, so sigma z of t, the difference between the occupation of the two states in the two-level system. And again, in all of the examples I'm going to show you, there's no bias, so epsilon is 0, and the initial condition is that we hold our system in one of the two states and then we let it evolve. So here's a comparison with an numerically exact multi-layer, multi-configuration, time-dependent Hartree method. The results in black from this paper are at 0 temperature. We compare it with a very low temperature with our method, and we see really excellent agreement for both expansions in this across different values of the sub-Ohmic exponent in this strong coupling regime. So now let me show you some of our results. And again, I'm going to focus on the population difference. So this is kind of what a typical evolution of the dynamics looks like. Alpha here is the coupling constant. So the greater alpha, the stronger the system is coupled to the bath. And depending on the strength of alpha and on the value of the sub-Ohmic parameter S, we can have different types of behavior. So one thing we notice is that at long times, we can either converge to 0, so the system becomes delocalized, so it loses memory of its initial state, or it can retain some memory and it can appear to be localized, so have a higher probability to be found in the initial state than in the other state. At shorter times, we see there's a distinction between coherent oscillations and incoherent decay. So that is another interesting feature that we're going to look at. Now, it is known that in equilibrium, the localization, delocalization regimes are separated by a second-order quantum phase transition in the sub-Ohmic regime and a Kosterlitz-Thalles phase transition in the Ohmic regime. But what I'm going to talk about today is what can we learn about the system, specifically from the short and intermediate time dynamics that we can compute with the inchworm real-time quantum Monte Carlo algorithm. So let me show you a bit more detailed picture of the dynamics. So what I'm plotting here, it's essentially a density plot of the same plot that we had here, but now we have two axes, the time axis and the coupling. On the left-hand side, we have the low temperature regime, and on the right-hand side, the high temperature regime, and on the top, we're very deep in the sub-Ohmic regime, so S equals 0.2. On the bottom, we're closer to the Ohmic regime, S equals 0.8. And so we can see the following things. So as expected, we can see that as we increase the coupling, the system becomes more localized. And the shaded region here marks the approximate location of the localization-delocalization transition as we see it from short and intermediate times. And you can also see that the greater the value of S, the larger the coupling is needed to get to that transition. We can also see that oscillations become suppressed as we increase the coupling. So that's also not surprising, but perhaps what is surprising is that we see two different mechanisms at work here that cause the suppression of coherence. One is that, well, the amplitude becomes more damped as we go to larger coupling, but we can also see that there's a change in frequency. And this change appears much more noticeable here deeper in closer to the Ohmic regime than it is deep in the sub-Ohmic regime. So in the sub-Ohmic regime, the frequency remains mostly unchanged, but as we get closer to S equals 1, we see that there's a noticeable change in frequency as we increase the coupling. And so it's really fascinating to study the interplay of these two mechanisms that cause the loss of coherence in the system. And to my knowledge, this hasn't been studied before in this context. When we look at the high temperature plots, then we see that, as expected, the system becomes less localized and less coherent at higher temperature. And we can also see how there seem to be some differences again in how the frequency changes and how this delocalization and incoherence transitions happen. So because the inchworm method works very well across a wide range of temperatures, we are in particular interested in seeing how does temperature affect the dynamics, what happens to these transitions, and how can we explore these phenomena further. So this is what I will focus on in the rest of my talk. Now, how do we analyze our data? We do heuristic fits of our simulation data. So these fits have been found to describe the data at short and intermediate times really well. Essentially, all we do is we fit to a damped oscillation, to a damped cosine, plus an exponential decaying term, plus we allow for a constant offset that would mark the distinction between the localization and the delocalization transition. And here examples of two fits where you can see that heuristically these fits describe the data well, and they will allow us very nicely to extract the oscillation frequency, various damping coefficients, and to distinguish between localization and delocalization. So let's look at the localization transition first. As I mentioned, it is known that at zero temperature, there is a quantum critical point in the sub-Ohmic case, and one expects this phase transition to be in the same universality class as the thermal phase transition of the classical Ising spin chain with long-range interactions. So a lot is known about this quantum phase transition, particularly the critical exponents are known. So on the right-hand side from this work, I'm showing you some results for this equilibrium known quantum phase transition with a critical exponent, with the corresponding critical exponents. On the left are our results for the localization transition as it is extracted from the short and intermediate time data. And you can immediately see that the picture is very different. So from intermediate times, and we call it the transient dynamical transition, it looks like the critical exponents are actually greater than 1, while the known exponent in this regime should be 1/2. So we would expect the offset not to increase like so, but rather have this really sharp square root increase instead. So this was very surprising to us because if we really look at short and intermediate time data, we will not see the same picture as occurs eventually in equilibrium, which takes a very, very long time to reach for the system. So these seem to be very different physical pictures at play, and I will relate that later on also to the initial condition, especially since in the last talk we heard so much about the role of initial condition and how do we retain memory of the initial condition and so on. Now, what about the loss of coherence? I mentioned these two distinct mechanisms that are at play that cause the loss of coherence, and in these plots we see them in a more quantitative way. So in this plot you see how the frequency changes as coupling is increased across different values of the sub-Ohmic exponent. And on the right-hand side, we see the ratio between the frequency and the damping. And this horizontal line corresponds to the frequency equaling the damping. So that's kind of the threshold when below which the damping starts to outweigh the frequency. And here we see kind of a smooth crossover for all values of S. Eventually, the damping will outweigh the frequency and we will lose coherence due to this damping-driven crossover. But if we look at the frequency itself, we see a very, very different picture depending on the value of S. So if we're deep in the sub-Ohmic regime, if S is smaller than approximately 0.5, then the frequency does not seem to decrease. It actually even increases a little bit at the beginning. But for larger values of S, there's eventually a very sharp drop of the frequency to 0 values. And this was more of the hallmark of a sudden transition than of a crossover. So not only do we have two independent mechanisms at play here, they do behave very differently because one kind of behaves like a smooth crossover and one like a sudden transition that only occurs for certain values of this parameter S. Now I summarized our results in this transient dynamical phase diagram. So we show the equilibrium localization transition from this work as these red solid circles connected by a line, and the corresponding transient dynamical localization transition with the error band from our work seems to agree well with it at small values of S, but then seems to deviate, especially at large values of S. So the stronger our coupling and the smaller our S, the more localized the system is. And conversely, on the other side, the system is delocalized, but this change happens very differently depending on whether we look in equilibrium or at short and intermediate times. And then the blue and the green line are respectively the two hallmarks of the coherence-decoherence crossover transition. The blue line is the frequency-driven transition, and the green line is the damping-driven transition. So in the last, and I did promise to mention the role of the initial condition. So I talked a lot about the equilibrium situation being very different from the transient dynamical situation, and that becomes especially apparent if we consider other initial conditions. So on the right-hand side from this work here, they used the condition where the system was thermalized together with the bath, but with the constraint that the system was fixed in one of the two states, and then it was let go at the start of the evolution. And on the left-hand side is our data for the factorized initial condition where the bath and the system were thermalized separately. And you can see how if we compare, so we would be comparing the green line here with sort of the average of these two lines here. In this situation, we reach delocalization much more quickly than in this situation. So if we assume, after infinite time, once we are in equilibrium, the initial condition shouldn't matter, so we will have forgotten all about the initial condition. It is absolutely not apparent what this equilibrium will be just by looking at the dynamics at the time scales that are accessible to us, because the dynamics is so different with these two different initial conditions. So that's kind of yet another instance of the transient dynamical regime being interested. And now finally, in the last part of my talk, I want to show you some preliminary results at a finite temperature that we will hopefully have out on the archive soon. So as I mentioned, we can use this method across all values of temperature, works well at low as well as at high temperature. And it's interesting to see how the dynamics changes as we increase the temperature. So here again, our dynamics density plots, but now with the temperature axis here. Again, the top is deep in the sub-Ohmic regime, the bottom is closer to ohmic, and the left-hand side is weak coupling. The right-hand side is close to where the transient localization transition happens at zero temperature. And again, we see that as temperatures increases, a system becomes less localized and it becomes less coherent. And there is a change in frequency as well, and it seems to have to behave differently depending on what regime we are in. So to look at it a little bit more quantitatively, we examined our various fit parameters. So we looked at the offset that characterizes the localization transition. When the offset falls off to zero, that's when we become delocalized. And we can see that, well, at higher temperature, as expected, the system does become less localized, but the transition itself also becomes kind of less clear. So if we look in the bottom panel, we have the offset versus coupling lines at different temperatures. And so the lower temperature, kind of the flatter these lines become, they still maybe have these kinks at the transition, but the kinks become less resolved. So it becomes actually a lot harder to pinpoint the location of this transition as we increase the temperature. If we look at the decoherence, then we also see some interesting things. So the damping-driven transition, kind of as expected at high temperature, it just moves to lower values of the coupling. So already at lower coupling, we will become incoherent if we're at high temperature, and everything seems kind of very smooth. So we observe this transition across all values of S and coupling. But something interesting seems to happen if we look at the frequency-driven incoherence transition. So before we had the sudden drop only at large values of S, but as we increase the temperature, we see that actually we can observe this sharp drop even at smaller values of S, and it also does happen kind of mirroring this picture at lower coupling. We also see a very strong increase in frequency at very low values of the coupling. Which is quite interesting. And kind of to summarize some of these findings here, some preliminary finite temperature phase diagrams. So kind of compared to the low temperature case, what we see as we increase the temperature going in this direction, while the localization transition becomes a bit harder to resolve, but it doesn't seem move significantly, but the location of the incoherence transitions, both frequency and damping driven, seems to change. So they seem to kind of move further down compared to the delocalization transition line, which may also be quite interesting. So I'm out of time, and this brings me to the end of my talk. A couple of other interesting things to look at in the future, apart from examining more closely the nature of the role of temperature playing on the dynamics, is we can generalize our model, for instance, by introducing two baths at different temperatures and look at the current through the system. We can even include some fermionic baths. We're interested in Anderson-Holstein model if we want to study these features of the system. It's also possible to map the Spin-Boson model onto an electronic system of a single site coupled to one or several interacting electron leads via mapping called bosonization. So that will be an interesting way to study interacting electron leads. So thank you very much for your attention. I hope I could convince you that the sub-Ohmic Spin-Boson model has many interesting properties and that its dynamics can be studied efficiently using real-time quantum Monte Carlo with the inchworm algorithm. We talked about the localization, delocalization transition at zero temperature, as well as two competing mechanisms for the coherence, decoherence transition or crossover. And we looked at how temperature changes the dynamics of the system. Thank you for your attention.
Thank you very much, Olga. Are there any questions? I think Marco is raising his hand. You can go ahead.
Thank you for the talk. I was wondering, so when you compare with the equilibrium transition, so the fact that that in equilibrium this is supposed to be the transition of the Ising model with long range is based on quantum to classical mapping, which you typically do in imaginary time. So is this maybe the reason why, obviously you're doing dynamics, right? So it's not clear at all that this quantum to classical mapping should work. I was wondering whether this could be the reason why this does not work, that in fact you find a critical behavior that is not the equilibrium one, whether this can tell us something about in general quantum.
So to my knowledge, all work on this phase transition, there has been a lot of work on it over the past decades. This was all done directly in equilibrium. So there's no dynamics entering any of these calculations. So it's just a symmetry breaking of the model. And there are many different methods also that can be used to study this phase transition. So I think that these results are very well established in equilibrium. And we do know that theoretically, if we do dynamics, eventually we should reach this equilibrium, but it is also known that it takes a very, very long time. So you can estimate how long it takes, and this time is not accessible with the method that I described today. So it would actually be very interesting maybe to look at some steady state methods or some extensions of this method. I see Andre in the audience, so we have been working with him and with Emmanuel as well, and maybe doing some fitting of the short and intermediate term data with an exponential expansion to try to better somehow get an insight over what happens at really long times. But sort of the point I'm trying to make is that it's a completely different picture that we see from short and intermediate times compared to what will eventually happen in equilibrium. And part of sort of what motivates me is thinking about maybe some experiments that are done with dynamics and that are done, thus by definition, at short and intermediate times. They might see very different phenomena than what is known theoretically to happen in equilibrium. And those also kind of reminiscent of a delocalization phase transition and come maybe with a semblance of their own critical exponents that are different. So that's sort of the interesting point of this analysis, in my opinion.
Thank you.
Next question. Olivier?
Yeah, I can ask. Slightly more yeah, can you hear me? Yeah.
Yes.
I was slightly more technical questions. I'd like to understand the limitation somehow of this method for bosons. I'm more familiar with the methods for fermions. And in particular, how does it compare to other methods like tempo, for example? You know, these techniques that's been used for a lot for bosons and where you decompose influence functional response networks in time, or has it been looked at?
I'm not familiar with that specific method, but yeah, there's a lot of other methods. And so I think here I showed the MLMC TDH method. So that's numerically exact at 0 temperature. There are methods, there's HEOM, there's QAPI, there's
they have different names. So
yes.
So they are, I mean, basically the inchworm is quite efficient in this for this kind of models compared to the other techniques. Or what are the trade-offs between these different methods?
So there are some methods that are better at high temperature. There are some methods that are very good at low coupling. You can also do some analytics at low coupling, which I didn't show very much, but so these dashed lines that you're seeing here, these are actually analytical predictions from an IG method. So it's from Stefan Kierein's papers. And they work very well at very low coupling. And but then I don't have plots here, but you can sort of see them already failing at large coupling.
Sure.
The inchworm method, so there are some regimes that are difficult, and so we have been discussing a lot the sort of is difficult equal interesting phases. So I had some difficulty actually at intermediate temperatures. So I'm showing you here kind of very low and very high temperatures. And at intermediate temperatures in particular, I had trouble making the two expansions, the diabatic cumulant expansion and to the hybridization-like expansion converge and also converge at all and agree with each other. I don't have sort of across all temperatures kind of good map of applicability in this paper here. In the second of these two papers, they discuss kind of applicability across different regimes for a combination of coupling. Yeah, sorry.
No, it's fine. It's fine.
Yeah.
Just it answered my question. Thanks.
Yeah.
I see Dennis wants to ask a question, so yield to him.
Yes, I have a somewhat similar question, but at the very end you mentioned that you could use bosonization of fermionic impurity problems and now apply your method. Do you see any advantages of using this? So in which regime do you expect that bosonization would help you with respect to standard, I don't know, hybridization expansion or stuff like this?
So we haven't implemented this yet. It would be a slightly different model. So it would not be exactly a mapping into the Spin-Boson model, but it would be a Spin-Boson model with some additional contribution. So the motivation was to study interacting leads. So you would have your single site, and then you could account for interactions in the leads. So sort of the motivation was that as opposed to non-interacting leads, there are situations where interactions in the leads can play a role. And so it would be interesting to see via this mapping what we can learn from a Spin-Boson-like model. And because this model is very simple, the bath is it's just a harmonic bath, so that would be a simplification.
Mhm. Mhm. Okay, I see. Thanks.